All right, guys, we are going to take a look at today's lesson from Monday, the 26th. And in this video, I'm also going to review the lesson for tomorrow, the 27th, because honestly, this should have just been one lesson. Let's take a look again at our Explore from today. We have Heidi spins my spinner shown here. I'm looking at my spinner. It has 1 through 5. I can assume that these are all equal, the 1 through 5 slices, if you will. Determine the theoretical probability of the spinner landing on each number. Record your answers in the table below. So the probability of landing on 1 is 1 in 5. Same for all of these. As a decimal, that's 0.2, which is equal to 20%. Oh, a little mistake up here. 5. So moving down, so how many times theoretically should she expect to spin each number if she does a total of 20 spins? All right, so if it was 1 in 5, I'm going to set that over 20. Okay, and so it's going to be 4 over 20. To get from 5 to 20, I multiplied by 4. To get from, so I'm going to multiply the 1 by 4. So each of these is 4 and 20. Which is also 0.2 and 20%. So explain my predictions. Well, why am I deciding how many times theoretically we should land on a specific number? So since each section of the spinner is equal, there is an equal likelihood that I could land on each outcome. And so when we have a theoretical probability model that we do, and we have an equally likely chance of landing on each outcome, we call that a uniform probability model. Let me go ahead and write that in a different color. A uniform probability model. Take a minute to review that. And we're going to go down to independent practice medium. Okay, cool. Mr. Longley is going to spin the spinner below. Again, I have a spinner that has 4 equal parts. Create a probability model showing all the possible outcomes of one spin. Okay, so in this case, I'm just going to make a really quick chart, just like we saw on the first page. I know my possible outcomes are red, yellow, blue, and green. And I know that each time if I spin once, I have a 1 in 4 chance of landing on each of these, which is equal to 0.25 or 25%. And now my question is this representative of a uniform probability model? So take a moment and think about that. And your answer that I hope that you got is yes. Because there is an equal each outcome is equally likely. And what we're talking about here is theoretical probability, and I'm going to post a link in the description box for you guys from Khan Academy on the difference between theoretical and experimental probability. But theoretical means I haven't done an experiment yet. I'm taking a look at my possible outcomes, and based on the total number of outcomes that I have, I'm going to decide the theoretical probability of the outcomes I should get. So making that a little, looking at this circle here, I said, okay, there are 4 possible outcomes, and each of those outcomes is 1/4, is likely to happen 1 out of 4 times. So my theoretical probability of landing on green is 1 in 4. Okay, I didn't do it, but based on this information, I can come up with the theoretical probability. So let's take a look. Mr. Longley does spin the spinner 100 times, and the table below shows where he landed. So this is his experiment. Okay. Sometimes you'll hear it called an event. So each time he spun the spinner, that would be one event. So I'm looking here. He landed on red 20 times, yellow 28 times, green 30 times, and blue 22 times. What could account between the difference? What could account for the difference between the theoretical probabilities and the observed frequencies of landing on each color? So theoretical probability are estimates. But they may not match the result. And I want to be clear with this math term that we see here, estimate. Okay, an estimate is not a guess. An estimate is based on the information that you have. So if you were to estimate anything besides that each of these would land 25%, before you've done an experiment, then your estimate would be wrong and your theoretical probability would be wrong as well. We're going to very quickly just take a look at number 1 in the homework, and then we will move on to different probability models. Nadine puts 4 blue, 4 red, and 4 yellow cubes into a bag. She wants to pick a cube from a bag at random as a probability experiment. Create a probability model showing the theoretical probabilities of picking each color. All right, so I have blue, I have red, I have yellow, I have 4 of each. So that's giving me 12 total. So the possibility of blue is 4 and 12. Red, same, 4 and 12. Yellow, 4 and 12, which is also equal to, each of these has the probability of 0.33 repeating or 33.3% repeating. Does this situation represent a uniform probability model? Well, what I'm going to ask myself is each outcome equally likely? And in this case, yes, it is. So this does represent a uniform possibility. Does, because outcomes equally likely. Cool. All right, so now let's take a look. Nadine performs this experiment 12 times and she records the results. she gets, it looks like here, 3 red, 4 yellow, 5 blue. So given that, I now want to create her experimental probability. So red, yellow, blue. Okay, so red was 3 out of 12, which is 25%. Yellow was 4 out of 12, which is 33.3% repeating. And then the blue is 5 out of 12, and that's one percentage I don't know right off the top of my head, so I'm going to have to divide. 5 divided by 12. Bear with me, I bet you'll get there before me. All right, so that's about 41.6%. What could account for the difference in theoretical and experimental probabilities? So again, theoretical is an estimate. Now, in the Khan Academy video that I'm posting in the description, Sal Khan talks about when you have thousands of events or thousands of experiments, meaning she didn't just pull yellow, sorry, what is it that she's experimenting on again? Okay, she didn't just pull the cubes 20 times, she pulls the cubes a million times. We do expect that you would get closer to your theoretical probability. So watch that video and it'll be really helpful for you to understand that concept. I'm going to pause right here. We're going to take a dive into tomorrow's lesson. All right, guys, I am back. We are going to talk about what we're going to do pretty quickly tomorrow, and that is a non-uniform probability model. And so we'll take a look at the frame. How can we calculate the probability when not all outcomes are equally likely? So we've been talking about things like our 6-sided die where it's 1 through 6, everything is equally likely. We've been looking at spinners where you have 1 through 5 and each sort of slice of the spinner is the same size. That's not always the case. So let's take a look at our Explore here to help us out. Miss Impink, Miss Shah, and Miss Faison are playing a board game with a spinner. They can only move their game piece if the spinner lands on their color. What is the probability of the spinner landing on each color? All right, so what is the probability of the spinner landing on each color? Each color. All right, so I'm looking over here and I have this yellow chunk and I have this blue chunk and then I have this much, much, much larger, sorry, I don't know what's going on there, red chunk, okay? And so for yellow, I think it's about 1/4, okay? So the probability is 1/4. For blue, my probability also looks like it's about 1/4. And my red, it looks like it takes up as much space as both the yellow and the blue. So for my red, it's 2/4 or 1/2. Okay, so right away, I don't have my, right away, I'm not going to have a uniform probability model. And I'm not going to have a uniform probability model because my outcomes are not all equally likely. So let's go down here. We can make some predictions. So predict how many times each color would be spun in 30 spins. Okay, so let's take a look here. And we'll do, let's see, we'll do yellow and yellow. I don't know how well you'll be able to see that. All right, so for yellow, my chances of yellow are 1 in 4. And so what are those chances out of 30? All right, so to get from 4 to 30, I would multiply by 7.5. Okay, so I have a 7.5 chance out of 30 of landing on yellow. Now with blue, again, I have 1/4 is equal to this sort of x over 30. I did by 7.5 to get there. Okay, you could also cross multiply. And again, I have a 7.5 chance of blue. 7.5. All right, now with my red, it's 2/4 or 1/2. Oh, sorry, I should do the red one. 1/2. Okay, if I set that equal to 30, okay, it's going to give me 2 times 15 gives me 30. It'll give me 15. All right. So my probability, and I'm just going to go to black ink here now. My probability of yellow, blue, red, probability of yellow is 7.5 out of 30. Blue is 7.5 out of 30. And red is 15 out of 30. Okay, and so basically it's a 25% chance, a 25% chance, and a 50% chance. So now, oops. Oh, this isn't on this page. But here's my question. Is this a fair game? If Ms. Impink, Ms. Shah, and Ms. Fossen are playing this board game together, is it fair? Or is somebody going to have an advantage? And in this case, whoever is lucky enough to be the red person is going to have an advantage because they're more likely on any given spin to earn a point. And so we have a non-uniform probability model and we have an unfair game. So let's take a look really quickly at our additional at-bats here. A traffic engineer records a sample of the types of vehicles that cross a bridge. She counts 76 passenger cars, 14 light trucks, and 15 heavy trucks. Okay. And then, so if you're trying to visualize, oh, light truck versus heavy truck, I would think like a pickup truck versus like one of those giant Mack trucks. Okay. So create the probability model to predict what would be the next type of vehicle to cross the bridge. Express each probability as a decimal or percent, okay? So let's see, I had 76 plus 14 plus 15, 76 plus 14 plus 15, okay, and that gives me 10, 15, 7, 8, 9, 10. Okay, so I did 105 trials. So my passenger car is 76 out of 105. My light truck is 14 out of 105. Okay, and my heavy truck is 15 out of 105. And since it had to be out of 105 and not out of 100, I am going to have to do some division to get the correct decimal. All right, so I do 76 divided by 1. Divided by 105. Okay, that's going to be 72.72. For 14 divided by 105, that's going to give me 0.13, like repeating a million times. Okay, and then for 15 divided by 105, that gives me about 0.142. So I'm just going to go to 0.14. And again, that would be 72%. 13, we'll give that a 13.3 repeating percent. You don't want to put a repeating over a whole number. And then 14%. Okie dokie. So let's take a look down here. which spinner could be used to best predict the type of vehicle that will cross the bridge next? Okay, so I know that if I go like this, if I choose this one, oh no. Okay, sorry guys. If I choose this one, that would be like saying it's equally likely that I would see a light truck, a passenger car, or a heavy truck. And that's not the case because that is not what was observed. And also, if you kind of think about it, most of the things you see on the road are actually going to be cars, okay? So we know based on the experiment that was done that this spinner is not going to help me. Now over here I have passenger car, light truck, heavy truck. And this is about 50%, and this is about 25, and this is about 25. So we're getting closer, but I'm still not convinced. For this one, let's see. I have definitely a little bit less than 75% here. All right, because if it was 75%, it would go right across like this. So I'm going to guess that this is about 70%. And then I'm going to guess that these are both about 15%. And over here, my passenger car, I have 75%. And then it looks like I have 12.5 and 12.5. So based on what I did up here, calculating my percentages, it looks like letter C would be my correct answer. Sorry, letter B. Go ahead. So letter B is going to be my correct answer because it is more representative of the results of the experiment I got. Okay, now if we were doing this and you chose letter D, because a lot of this is just sort of eyeballing it and guesstimating, if we were doing this and you chose letter D, but everything up top was correct. So for example, if this was a two-part problem and you did this part A correctly, but you did this part and chose letter D, I would accept that answer, okay? Because I feel like it's possible to go kind of both ways on that when you're looking at something and you don't have the percentages given to you. Okay. So from here, we're gonna say goodnight, and tomorrow we are hopefully gonna be doing 2 objectives at once. We're gonna do this non-uniform probability model, and then we will move on to our response to data lesson that we have planned. And I will see you tomorrow. Have a good one.